Hello everybody, this is Dr. Christopher White and welcome back for part 2 of our video dealing with the lab exercise stratigraphy. So we are now moving on to the second part of the lab assignment, so this is going to deal with biostratigraphy. So in this part we are going to be looking at a sequence of Ordovician age rocks from the United Kingdom which contain abundant graptolite fossils, and this is real world data from southern Scotland in the United Kingdom. Now, what we have is we have an interval of 85 meters, and within this 85-meter interval of rock, we have 14 different Ordovician graptolite fossils which have been identified. And this 85-meter thick unit of rock has been analyzed at 5-meter intervals, and every 5 meters, the graptolites which are present at that level have been noted. And so you can see this is the table here, which contains the information. So you can see the graptolite names over here on the left, and you can see their position in the sequence running along the top. So you'll notice that the first graptolite species is noted at 5 meters above datum, where we're starting from. And we can see that this particular species turns up at 5, 10, 15, 20, 25, and 30 meters above datum. And then by 35, it's gone. So what are we going to do with that information? Well, we're going to take all of the information from this table and we are going to plot it onto this figure right here. So you can see for this first fossil, whose name I'm not going to try and pronounce, I think that's probably best for all of us. I have already marked out the layers in which it occurs. So you can see the fossil name is written at the top here. So number one, make sure that the fossil name that you're looking at corresponds with the fossil name in the table of data. And you can see that this particular fossil occurs at 5, 10, 15, 20, 25, and 30 meters. And so I've marked its position in these layers of rock on the diagram. So for the first part, that's all you're going to do. You're going to take the information from this table here, and you are going to put it onto this figure here. And remember, each of the fossil species have their own individual columns, and the columns have been split into white or light grey just to make it even easier for you to make sure you know where you're looking. Okay, so once you have all of this information on this figure, what are you going to do? So for part 2, or should I say for question 2, sorry, you are then going to subdivide your stratigraphic column into biozones using graptolite ranges. So what you're going to do is you're going to use the ranges of one or more graptolite species to define biozones. So you can see that you are going to define 2 biozones. So the first biozone is actually going to be defined based on 3 separate graptolite species. So 1, 2, and 3. And so that means this particular biozone can only exist where these 3 species coexist. Okay, so that means that if they all turn up, if all these 3 species, let's say, turn up at 65 meters, then great, that's part of the biozone. If, however, at 60 meters only 2 of the species are present, that cannot be part of that biozone. In order to define a biozone based on 2 or more fossils, it has to contain all of those fossils contemporaneously. They all have to have been there at the same time. As soon as one of those 3 fossils disappears, that's it. You've left that particular biozone. And the second biozone you're going to define is going to be based on the appearance of N. Augustus. And so, for instance, you're going to look through your table here. So N. Augustus is there. You can see where it appears. So how are you going to put this information onto your figure? Well, you can see that a range zone has actually already been defined for you using the fossil with the name that I'm not going to try and pronounce. So if you look here, the range zone is defined based on the first appearance of that fossil and the last appearance of that fossil. And so because I am just defining this range zone based on 1 fossil, that's where the range zone begins and starts. Begins when it first appears, stops when it last appears. And so you can see what I've done is I have drawn a couple of lines, one marking the start of the range zone and one marking the end of the range zone. And I've also labeled the biozone as well to make sure that it's clear what I am trying to show. And so you're going to do exactly the same thing for the other two biozones. I'm just going to say this again to make sure it's very clear. The first biozone you're going to try and define is going to be based on the presence of free fossils. The biozone itself can only occur when the free fossils are occurring together in the same layer. All right. If you've got two or only one of the fossils, that's not the biozone. The biozone must have all three of those fossils in the same layer. Okay. So for question 3, what you're going to do then is you're going to color each of the biozones on the stratigraphic column on the right-hand side of the figure. So as we come over here, we can see for the biozone that we've already defined, that particular biozone has been colored in on our stratigraphic column, in this case red. So for the other two biozones, you're going to pick different colors, blue, green, maybe, I don't know, whatever takes your fancy. Now, the one thing I will just point out is you will notice that the biozone itself doesn't correspond to the boundaries between the different rock types. And so this is one of the things about biozones. They don't actually have to correspond to the lithologies, because what you're doing is you are defining a zone based exclusively on the fossil. You don't care about the rocks the fossil is occurring in, you just care about where does the fossil first appear, where does the fossil last appear. And so if it first appears halfway through this layer of sandstone, that's where your biozone starts. So that doesn't make any difference. So, the lithology doesn't make any difference to the position of your biozones. Okay, so for question 4, do the range zones match up with the contacts? No, they don't. We just discussed that. Okay, question 5. So what you're going to do for question 5 is you're going to give 2 examples of a graptolite species that only occur within one biozone. All right, so of these 14 species, there are going to be at least 2 examples where that particular species will only exist in one of the biozones which you are defining. And so you're going to name your 2 examples here. So for question 6, you are then going to give an example of a graptolite that was used to define a biozone, but also occurs within another biozone. So for instance, let's say the graptolite, which I will not be naming, happens to also stretch into another biozone. That would be an example that you could use. Now remember, when you are trying to name a graptolite that has been used to define a biozone, you can only use the graptolites that have been used to define the biozones. You can't pick any of the other graptolites. So your choice is relatively limited. So, look around and see if you can work out, which one or more species I'm talking about. Now, for question 7, it asks you how many graptolite species are present in each of the biozones. So you're simply going to count up how many species are present in each biozone. Now, let's say you have 2 biozones that are in contact with each other. So let's say, for argument's sake, the first biozone ends here at 30, and then the second biozone starts at 30. So the 2 biozones are in contact with each other. Well, if you have a graptolite species which falls on the boundary between those 2 biozones, that is considered to be part of both of the biozones. So you'll count it for the first biozone and you will count it for the second biozone as well. And so that's it. So part 2 is relatively straightforward. It's just all about splitting up this stratigraphic column into biozones using the graptolite fossils that we're interested in. Okay, so now let's move on to part 3. So this part is going to deal with graphic correlations and chronostratigraphic correlation. Now, in terms of using chronostratigraphic correlation as part of a lab exercise, it's not really going to teach you that much, because if you imagine you would have 2 stratigraphic columns, you would pick a layer of rock that was, let's say, 400 million years old in column A, and then in column B you would find another layer of rock which is 400 million years old, and you would draw a line in between them, linking them up. So, there's not really much you can do with that. But What you want to ask yourself is what happens if you are in a situation where you do have a definable age at some point, but you can't really date the rest of the column using geochronology. So in that case, one of the methods you can use is a graphic correlation. So a graphic correlation works by analyzing the stratigraphy at two locations, location X and location Y. So at both of those locations, you will have a datum to mark your starting point, and that will typically be, well, it can be a biozone ending or starting, or it can be something like an age, a numerical value, so geochronology. Now, how this works is for each location, you are going to produce a stratigraphic column, and you are going to go through that stratigraphic column, noting all of the fossils that are present. You are going to note the first appearance for each fossil and the last appearance for each fossil. So if you have a fossil that occurs at both locations, you can use it for the graphic correlation. So in this instance, let's say that 0, our datum, is based on a chronologic age. So let's say, once again, 400 million years. And so we know where we're starting from, and then we're going to come up from this datum to 100 meters above datum. And so this is the package of sedimentary rocks that we are going to be analyzing. So what we've done is we've gone through these stratigraphic column at both of these locations. We've marked the fossils. As you can see, we have fossils A to J. Okay, and for each of those fossils, we have the starting location and the end location at both locations. So, for instance, for fossil D, we know that fossil D first appears at location Y at 10 meters above datum. We know that fossil D also appears at location X, first of all, at 10 meters above datum. And we also know that fossil D last appears at location Y at about, let's say, just going to quickly eyeball it, 28 meters above datum. And at location X, it occurs at around 38 meters above datum. So what we're doing is we're using the value above datum for the first appearance of the same fossil to mark its position on a graph like this. And so you're going to mark the first and last appearances of each of the fossils that occur at both locations. And typically when we do this, we assign a different symbol to the first location and the last occurrence. And we also make sure that the points are clearly labeled so we know which fossil we're dealing with. Now, once you have drawn all the first and last occurrences for each of the fossils, you are then going to put a trend line through that data. And of course, it's going to be a line of best fit, so it doesn't have to be a line that goes from each of the points. It's going to be a line that simply goes through the majority of the data. And this is going to be your line of correlation. And so at location X, let's say we have a distinctive layer of rock which is located at 65 meters above our datum. Okay, now we don't obviously have a numerical age for this layer of rock, but we want to know where it correlates at location Y. So how are we going to do that? Well, what we can do is we can take our starting point at location X, which as mentioned is 65 meters above datum, and we're going to come off the x-axis. We're going to draw a vertical line until we hit our line of correlation. And the point where we hit the line of correlation is referred to as the point of correlation. And then we are going to move horizontally from the point of correlation until we hit location Y. And you will see that at location Y, we have a layer of rock which correlates at 50 meters above datum. So by using this method, what we're doing is we're using the fossils to correlate layers of rock at two different locations, even though we can't numerically link them. But because we have this numerical age that allows us to set the datum, essentially 0, which is the point above which we take our measurements from, it allows us to say, right, although we don't have a numerical age for this layer of rock here, we know it has the same age as this layer of rock at location Y. So as you can see, it's a relatively simple but powerful tool to correlate layers of rock at two different locations. Okay, so what else can you do with a graphic correlation? Well, actually, I'm going to keep that graph there on the right, and we're going to have this graph here on the left. So another thing you can do is you can analyze the rate of sedimentation at the two different locations relative to each other. Now, once again, this isn't going to produce a value, but you're going to be able to look at them and say, well, how fast is sediment being deposited at location X versus location Y? And so, as previously mentioned, once you've plotted the first and last occurrences for each of the fossils and you've put your trend line through, your trend line is going to give you some information about the comparative rate of sedimentation. So for instance, here is a graph that shows you 5 different occurrences, 5 different things that you could see with your line of correlation. So in the case of the black line, you have a perfectly equal rate of sedimentation. So you can see that the black line simply just goes up at the same rate for both locations. So there's nothing particularly special going on there. Now, if, however, your line of correlation is shallower, like the green line here, so it's more towards the x-axis, that indicates that the rate of sedimentation at location X is higher than location Y. So more sediment is being deposited at location X, so more sediment is being deposited more quickly at location X versus location Y. And of course, if your line of correlation falls closer to the y-axis, it's the reverse situation. So that tells you that more sediment is being deposited at location Y than location X. So therefore, location Y has the higher rate of sedimentation. Now, another thing that can sometimes happen is if you have a change in the rate of sedimentation. So in the diagram that we've drawn here, our line of correlation is just a single straight line. However, you may notice in your data set that, let's say you have a good line of correlation that comes up here, and then when you hit this point here, let's say maybe you have a load of fossils that suddenly start plotting on a new trend up here. Now that's telling you that there has been a change in the rate of sedimentation. So in the case of the red line, what can we see? Well, the first thing is we can see that the red line is located more towards location X than location Y. So for this portion here, from 0 to the change, that's telling us the rate of sedimentation is higher at location X versus location Y. Now then, at the point where we see the change, we see the line suddenly becoming steeper. This is telling us the rate of sedimentation at location Y is now higher than location X. So when you're plotting the first and last occurrences for the fossils on your graphic correlations, please take a second and keep an eye out for any obvious changes in sedimentation rate. Now, the final thing you might see with your line of correlation is if there is some kind of horizontal portion. So if we look at the orange line here, you can see we have sediments being deposited at at a faster rate at location Y versus location X. And then all of a sudden, you can see we have a horizontal portion, and then we have sedimentation occurring again. Now, this horizontal portion will not display any fossils. So what you're going to have is along this part of the trend line here, you're going to have a whole load of first and last occurrences for fossils, which occurred at both location X and location Y. And then you're also going to have a load of first and last occurrences for fossils that occur at location X and location Y for this portion of the trend line. But in this portion here, you're going to have a gap where there are going to be no first or last occurrences. And so when you draw your trend line, you're going to draw your trend line up here for the first group of fossils, first group of first and last occurrences, and then you're going to draw another trend line here for your second group of first and last occurrences. And then you're going to draw a horizontal line, which is going to tell you that there has been either an unconformity, i.e. erosion has taken place, or there has been a hiatus in sedimentation. So sedimentation has stopped at one of the locations versus the other. So in the case of the horizontal line resulting from a hiatus in sedimentation, what's happening is you have sedimentation at location X and location Y during this first portion, and then sedimentation is stopping at location Y. And of course, that means the amount of sediment isn't changing, while sediment is being deposited at location X. So you're suddenly moving horizontally across, and then sedimentation reoccurs, restart, should I say, at location Y, and then your line of correlation is going to continue upwards again. So by analyzing the changes in the line of correlation or the angle of the line of correlation, it can give you some information about what is going on at location X and location Y with regards to the rate of sedimentation. So there's, another piece of information that you can get by using a graphic correlation. So, okay, so let's move on to the questions. So for question 1, we are going to be looking at the information contained within this table. So you can see we have species A to I, and for each of them, we have a first appearance at location X and location Y, and a last occurrence at location X and location Y. And so you are going to plot this information onto the provided graph paper. So for each of the tables of data, a piece of graph paper has been provided, and in the title or for the particular figure, it will even tell you which table you are supposed to be taking your data from. So for question 2, once you've plotted up your data, you're obviously going to put your line of correlation through the data that you've plotted onto the graph paper. And then it's going to ask you which location has the higher rate of sedimentation, location X or location Y. So that's going to, of course, be based on the angle of your line of correlation. Is it closer to the Y-axis or is it closer to the X-axis? Then for question 3, it's going to ask you what stratigraphic level at location X corresponds to 60 meters at location Y. So if we go back to the example diagram, which is located here, you can see in this case, the layer of rock we were interested in was at 65 meters above datum at location X. In this case, the layer of rock that we're interested in is 60 meters above datum at location Y. So you're going to start your line at 60 meters above datum at location Y, and then you're going to come across until you hit your line of correlation, and then you're going to come down to the X-axis, and then that's going to give you the height above datum for the rock layer of the same age at location X. Let me come back down to the graph paper. There we go. Okay. So for question 4, we're then going to use the next table of data, which is this one here. So that's species A to J. Once again, first and last occurrences. You are then going to plot that onto the provided graph paper. And then for question 5, it's going to ask you, does the graphic correlation shown show a constant rate of sedimentation at the 2 locations? So does it show you a nice single straight trend, or does it show you maybe a change in the rate of sedimentation? And so you're going to have to analyze, does it look like the line of best fit should just continue as a straight line? Does it look like the line of best fit should maybe change angle? And then for question 6, it's going to ask you, after the change in sedimentation rate has occurred, well, that might be a bit of a hint for question 5 there, is the rate higher at location X or location Y, or is it approximately equal? So you will have to draw your own conclusions for that. And finally, for question 7, we're going to be using this final table of data here, which once again, you are going to be plotting onto the graph paper provided. And then we have question 8, which is going to ask you to analyze the data that you plotted as part of question 7. So question 8 asks you about the line of correlation, and the question itself tells you there's going to be a vertical or horizontal portion to the line of correlation that you plotted. This is obviously going to suggest there is maybe an unconformity, or there has been some kind of hiatus in sedimentation. So when you look at your graph, you're going to see that you have 2 distinct sections where the data is plotting. Each one of those areas is going to get its own distinct trend line, and then there's going to be a horizontal or vertical line which will link those 2 trend lines together. And so obviously this is going to be your hiatus in sedimentation or your unconformity. And then, so for question 8, you are simply going to have to look at that horizontal or vertical portion, and you are going to have to work out, where did this hiatus occur? Was it location X or was it location Y? All right, so that's it for the lab exercise stratigraphy. Thank you for watching and have a good day.